You've probably seen this 1,000 times in your terminal. You type LSL, and there it is. A cryptic string of letters and dashes sitting right at the start of every line. Something like dash, R, W, X, R, dash, X, R, dash, dash. Most people just gloss over it. But this tiny 10-character code is actually the gatekeeper of your entire Linux system. It controls exactly who can read your files, who can modify them, and who can execute them as programs. Every single file and directory on Linux has one of these permission strings. And every single time any process tries to access any file, the kernel checks these bits before allowing anything to happen. So what do these characters actually mean? Let's break it down, piece by piece. Every file in Linux has 3 basic permissions: read, write, and execute. Let's look at each one. Read permission, shown as the letter R, means you can view the contents of a file. You can open it, cat it, or copy it. Write permission, shown as W, means you can modify the file. You can edit it, append to it, or truncate it. Execute permission, the letter X, means you can run the file as a program or script. Now here's where it gets interesting. For directories, these same 3 letters mean something slightly different. Read on a directory lets you list what's inside, like running ls. Write lets you create new files, rename them, or delete existing files within that directory. And execute, this is the key one, lets you actually enter the directory with cd or traverse through it to reach files deeper inside. Without execute permission on a directory, you can't even access the files inside it, even if you have permission on the files themselves. Now those 9 permission characters after the file type aren't just one set. They're actually 3 groups of 3, and each group applies to a different category of users. The first triplet is for the file's owner. The second triplet is for the file's group. And the third triplet is for everyone else, which Linux calls other. Let's say Alice creates a file, and the file's group is set to developers. The permissions read RWX, R-X, R-. Here's what that means in practice. Alice, as the owner, gets full access. She can read, write, and execute. Bob, who is a member of the developers group, can read and execute the file, but he cannot modify it. And Charlie, who is neither the owner nor in the group, can only read the file. Nothing more. Every file on Linux stores exactly 2 ownership values: a user ID for the owner and a group ID. That's all the kernel needs to decide which of the 3 permission sets to apply. There's a neat shorthand for writing permissions as numbers instead of letters. Each permission maps to a value. Read is 4, write is 2, execute is 1. You simply add them up to get a single digit for each category. So RWX, that's 4 plus 2 plus 1, which equals 7. R-X is 4 plus 0 plus 1, which is 5. And R-, is just 4 plus 0 plus 0, which gives you 4. Put those digits together, and the permission string RWX, R-X, R-, becomes 754. To change permissions, you use the chmod command. For example, chmod 755 sets the owner to read, write, and execute, and gives both the group and everyone else read and execute access. This is the most common setting for executable programs and scripts. You'll also see 644 a lot. That means the owner can read and write, and everyone else can only read. Perfect for regular files like configuration files or documents. There's also a symbolic syntax. For instance, chmod u plus x adds execute permission for the owner, and chmod g-w removes write permission from the group. So what actually happens when a process tries to open a file? The kernel runs a surprisingly simple decision tree. First, it checks, is the process running as the file's owner? If yes, the kernel looks only at the owner permission bits and nothing else. If the owner bits allow the operation, access is granted. If they don't, access is denied right there. If the process is not the owner, the kernel asks, is the process in the file's group? If yes, it checks only the group bits. And if neither of those match, the kernel falls back to the other bits. Here's the critical insight that trips people up. The kernel stops at the first category that matches. If you're the file owner, but the owner bits say no read permission, you will be denied, even if the group or other bits would have allowed it. One category, one check. That's the entire algorithm behind Linux file access control.